Okay, so good morning, everyone. How are you today? So before I start, remember, if you register for dinner, you have to talk with me during the break, okay? So I can take notice, because I have to call the restaurant to see how many you are. And if you didn't, just let me know if I know how many they are, I can, put more people. Okay, I have a limited number, but if someone is not coming, there are a couple of people say no, so I have a couple of that I can put you in, okay? So the dinner will be tonight by the beach. It's not very hot, but it's really cold, but that's okay. So, and please also sign on the entrance so I can argue that a lot of people come to these workshops and get more money for the group for doing more things like this. So today, this morning, I start, so I don't have to have my invited persons come early in the 9 o'clock in the morning, so I decided to put myself at 9 o'clock in the morning, and I'm going to talk about iterated local search and hybrid local search and other extensions. So that's what the talk. So we have until 11, and then we have a break, and then we have Belen coming and talk on application of Metaheuristics. She's coming abroad, so thank you so much, Belen, for coming. Okay. So this is a little bit the outline of the talk. So I will do introduction to Metaheuristics and iterated local search, some history, applications, and then the hybrid and extensions that we are working on the iterated local search together with a couple of colleagues, okay? I think I have to stay here so they can see me. There's a lot of people looking in streaming. I was surprised, so that's very good. Okay, so I start with a citation from Saramago. This is a book, and when I read this book, it says, how do you should search? When you search for something, how do you search for something? And they say you advance methodologically and with discipline. So search is not like an ad hoc thing. You have to have some discipline to search for something. If you don't know, this is a book called All the Names, where he's looking for the last name, the history of last name of someone, okay? So this is exactly what I like about Metaheuristics. We have some we have some methods that are well structured, and we have some discipline. And that's what we will apply when we try to look for the best solution of the optimal solution. This is my translation, so if it's not correct, it's my fault, okay? Because of course I read it in Portuguese. So, as I mentioned yesterday, introduced yesterday the combinatorial optimization. That's what I work. I usually try to solve problems of combinatorial optimization with Metaheuristics. Of course, Metaheuristics can apply to other type of problems, but I've never applied to other problems. I usually apply to combinatorial optimization, so I review yesterday the combinatorial optimization, but you can apply for global optimization, no smooth optimization, some discrete optimization, so this is a lot of applications. And this is the problems I presented yesterday, the ones I like to apply, from routing, scheduling, it's the ones I apply most, but also for click, and I've done something for cloud computing. I confess it was very challenging for me because I didn't know anything about telecommunications. So we spent a lot of time trying to have a common language, and then after we have the common language, everything went smooth, okay? So this is the areas that I already mentioned yesterday. How do I apply it? From healthcare, marketing, manufacturing, logistics, transportation, and telecommunications. Okay, so there's two worlds on combinatorial optimization. People that like to do the model in intelligent programming and solve it with exact methods, Lagrange regularization, cuts, anything that you have on this world, and people that like to do this, okay? To do this local search and Metaheuristics. These are tools, so you should use your tools the best way possible. If your problem can be solved with this, you can solve it with this because we have a warranty of obtaining the optimal solution. But sometimes, and most of the real problems that I deal with, I cannot get this. I have to look for some other areas. Some people say, oh, but you should study more and try to get some optimal solutions, some theorems, some things. Yes, but then it will take me forever. It will take me 5 years of research, and the problems are to be solved now. I cannot go to the business and say, I'm sorry, I need more time to study your problem. No, we need to answer. And that's also research, to be able to answer problems that appear in reality in a very fast way, and they can apply them and they can use it. Okay? So this is a little bit, I think we should know at least something about the both worlds if you wanted to be able to apply these techniques to real problems. Okay? Some definition of what is a heuristic. So a heuristic, and you can find this term in many other disciplines, it's like a set of rules to obtain one solution. So you get a set of rules to obtain a solution. You reduce complexity because you don't have a warranty of obtaining the optimal solution, but you get it on the running time. So the running time is reduced. And the Metaheuristics is more than a methodology that goes over the heuristic. It's like a methodology to design heuristics to solve a problem. Okay? It's finding a good solution, applying some steps, and having subordinated an heuristic. Okay? And this is Ranfai, the person who should be here today, and unfortunately cannot do. So we could explain this better than myself because he's the one who wrote the definition. Okay? So we have a lot of Metaheuristics. Okay, we have a lot of Metaheuristics. Everyone has his favorite Metaheuristic. So if I work in GRASP, I always apply GRASP because it's one I feel comfortable. If I'm working in VNS, I apply VNS. I'm very much against this new trend to have new names for Metaheuristics. So if you write a paper with a new name for Metaheuristics, ends up in my desk for referee, you have a clear reject. Okay, I cannot. So I'm very much against having these weird names, and I even don't like to repeat it because I don't like to make publicity to them. This is hurting very much the area. Okay? If you invented something new, maybe you can name it, but it must be something new, because I've seen lots of new names call for things that exist for many, many years. So the heuristics, I think the oldest paper I have in heuristics is from the 50s. Okay, so it's not something that is new. Okay, this just shows that the person, and sometimes the advisor of the person, which is worst, does not read the bibliographer review, does not have knowledge on the area. So be careful with using these new names, because it's most of them are structured. I've seen very few things on the structure lately. Okay? Even there is some few things, but sometimes it's just renaming something that exists. So anytime you go to design an heuristic, look very careful on the literature, which is becoming more difficult because there is more literature now than 10 years ago. But you should be very good on literature. So these are, and I do recommend a paper from Ken Sorensen in the Iterate journal where it does explain this. And he has a web page where he puts this. Okay? There is some people, for example, I see a paper from computer science, they claim they invented local search. Okay? So local search, if you know, it's very, very old. Okay? So this is very careful, especially for young people. If your advisor is good, fantastic. If it's not good, sometimes we are not good as advisors. And you should really do your work. Now you have access to internet and look for things before you start to put weird names like flying elephants. Okay, I did say one, which I think is absurd and is hurting the area. It's hurting every one of us, even the serious people that do work on this and are very serious researchers. So these are some well-known algorithms. Of course, I'm going to explain you my favorite one. As I said, everyone has a favorite Metaheristic, okay? So why do I like Metaheuristics? As I said, I work with real problems. They are much more complex than what I call the toy problems. I call this TSP as a toy problem. It's when I give my kid a toy so he can learn, some coordination. This is a toy. So then in the future, he can be a coordinated person. Or when I give them a book to learn colors, that's a toy. So we can recognize the colors in the real world. So these are very complex. And also, they change very rapidly. So some company has a problem in routing today. Next year, they come out a new technology that they can identify very clear, what time the customer is, a new app, and the problem is changing. So you need a solution that lasts for a long time, not a solution that you give a solution today. Next year, there's new constraints for that problem, and then you have to do research again. So if you do a branch and bound, a specialized branch and bound to solve this problem, if there is new variables or new constraints or new objective function, you have to redo everything again. Need a quick implementation. Okay, you need, I think I mentioned yesterday, there was some software that takes 30 years to be developed. It's the best software in the world for TSP, the Concord, but it was 30 years of researchers working on that. So you cannot go to any application for this. It's not the same, for example, to give you an example, routing is not the same routing for an e-commerce than routing for a traditional commerce. It's completely different. Characteristics are different. So you cannot just have like a general software and you apply it. And most of the times you don't need to have the optimal solution. You need to be able to answer questions like, what if the traffic is high? What if it's raining? What if it's... And be able to give answers so the decision maker helps the decision maker to make decisions. So this is the characteristics of real world, and this is what's the characteristics of the Metaheuristics. There's highly effective on hard problems. So in very hard problems, we can obtain very good solutions, and that's what researchers do. We try to design algorithms and prove that they are very good. They have modularity. So it's like a Lego. So I can recycle some of these Lego pieces for next algorithm. Some of them, and this is, I'm going to talk about this, is easy to implement. It's much easier to implement than some others. So it's easy to do short updates, are robust. So the solutions they come are real robust, and they give good solutions in short time. So that's what makes Metaheuristics ideal to solve the real problems. How do you measure how good is a Metaheuristic? Because, of course, I cannot measure to get the optimal solution because I don't have mathematical warranty that it's the optimal solution. So how do I measure? The most common one is accuracy. How close is to my optimal? Okay? Sometimes you have also speed, small computational time. So I can solve real problems in seconds. But I like this too, which is not so common. And this is a nice work from these people in Canada. It should be simple to implement. I used to say that, okay, if you have, I've seen a paper with 30 parameters, I have 30 parameters, and then I'll do adjust parameters every time to run. And someone in the room, a person that knows about machine learning, said, oh, you have to apply machine learning, and then we define the best parameters for this problem, and then you run the algorithm. If I have 30 seconds to run the algorithm, can I do that? No. If I have 5 minutes, no. I can do this in theory, maybe, but no. If I don't have that data, if the data is new every day, don't have real history, it's complicated. So I like simplicity. This is kind of interesting. And then flexibility, it's also another characteristic that I measure quite well in the Metaheuristic, which is how easy it is to adapt. Okay, how easy to adapt if the problem changed a little bit. So this is related with these quick changes. How easy it is to adapt to a new situation. Okay, so I like this 4 characteristics. So if you write the paper, try to justify this. You can cite these people. Say, my algorithm is good, obtains a very good solution, it's fast, it's simple, it does not have too much parameters and can be adapted very well because if the objective function changes, I just have to change this function and everything will work well. Okay? So starting with the most basic concepts in Metaheuristics that I'm sure that you know, but I'm going to review them because there's some people that start here from scratch. The most basic concept is the neighborhood. So we always try to find solutions that are good on a neighborhood. What is a neighborhood? So a neighborhood are solutions that are obtained from a starting solution by changing a little bit, what is called a move. So I changed this solution a little bit, and I call this is a neighbor of my initial solution. And of course, the theory between this is the local optimal. So the local optimal is the best solution for all solutions on the neighborhood. Okay? So this is the most basic concept in not all Metaheuristics, but in many of them is the neighborhood concept. So definition of neighborhood is essential to define a good Metaheuristic. And of course, in one of these Metaheuristics, the search strategy gives the name to the Metaheuristic, okay? So, of course, this is the local op search. This, as I said, I think I have a paper from David Johnson from AT&T from the 60s or 50s, I don't remember anymore. I have them, that's one I don't throw to the garbage. I have them there printed, okay? When he uses local search to solve the TSP. And then there was the Kinlin-Kernighan algorithm, which is quite even still good for the TSP problem. Okay, so it's just you get a solution, you can add like a constructive heuristic. Most of the problems here we can construct. That's what people in the business do. That's what they do, for example, when they want to construct your course scheduling. They get all the lists of scheduling, they start putting them. Okay, this is a constructive heuristic, so you get a solution, a feasible solution, and then you start improving this solution using this neighborhood concept. Okay, here you can have two types of search. It's like I get all the neighborhood and get it the best, complete search, or I search one by one, and as soon as I get one better, I restart from this new solution. Usually the second one is better than the first. Okay, that's the idea. Okay, so to implement a local search algorithm, you need to get initial solution, an heuristic, usually a constructive heuristic. You can even add a random solution. Usually it's not, it takes more time to go to a local optimal if you get a random, but you can start with a random solution. So you have a procedure to get the initial solution. Then you get to define what is your neighborhood, what do you define, this solution is close to this solution, and how do you search from complete to first improver. With these three modulus, you can construct a local search algorithm, which is surprisingly, most of the times is pretty good. Surprisingly, business understand this very well because they used to do this in an informal way. They get a solution, then they try checking. So if, for example, I observe what people do course scheduling in the university, that's exactly what they do. They start doing this. So it's an algorithm that business people can understand. Because another recommendation is that if the business people don't understand what you do, you are dead. Okay? They have to understand a little bit. Okay? So what's wrong with local search? What's wrong with local search is that in many of special combinatorial optimization, there's a lot of local optimals. So you get stuck very soon. Okay? So for example, in scheduling, I work one time, I calculate how many local optimals I find, and it's almost 50% of the solutions were local optimal. So if you get in a bad local optimal, you have the bad luck to get in bad local optimal, you're dead. Your solution is not good. So that's why it's a drawback of this, getting on a bad local optimal, and you cannot advance because you finished as soon as you get a local optimal. So one idea, an obvious idea, a very simple idea is to start in different parts of the region and go down. Okay? So you start on different parts of the region, start with different initial solutions, and then you get local optimal. And you repeat this called multi-start. Multi-start, you get initial random solution, you do local optimization, you see how it's better or not. If it's better, you keep it, and you repeat this many, many times, okay? So this is obviously the bad idea. What is the problem? That most of the random solutions are not very good, okay? So it's not very good. So one of the algorithms that also has this structure, as I said, that's why I said most of the algorithms are based on the same structure, so we don't have to invent new names for the structure, is GRASP. GRASP what it does is here you start with a constructive random solution. So you construct, but you put some randomness there. Okay? It's not totally random, because totally random, it can be really bad. So that's why GRASP, I think it's a very good algorithm too. I like it very much because it's very simple. It's very simple. You don't have to need any sophisticated algorithm. It's very simple. The only difference with this multi-start is that you start here already quite good, because you do a constructive and you do randomness. So for example, when I put, if I have to do like routing, I say, what is my, I'm in Barcelona, I have to visit all capitals in Spain, what is the closest capital? Okay, I'd have to go, I don't know, Tarragona maybe it's the closest one city, big city here. So, but I do a randomness. I do a random. I choose random amount, a certain number of cities, and I go there, and then I don't have always the same. So when I repeat this initial solution, I don't get always the same. So it's a kind of extension, a good extension of multi-start. Okay, so that's why GRASP is very successful, it's very easy to implement, and it gets very good results too. Because you have local search already, you just have to do this, put this randomness in the constructed heuristic. Okay? So then when we get also to iterated local search, which is another idea which is similar to this one. So as you see, GRASP and iterated local search all come from this structure, but we start in a different, we will start in a different way. We decide that we will start in a different way. The idea is that when you get a local optimal, you perturb that solution. You make like a chalk to that solution, so you get a different solution, then you repeat again. Okay, so in the GRASP, they do constructive heuristics, putting randomness on the constructed heuristic. Here we use the last local optimal C, but you perturb this doing a big transaction, a large step, so to restart again. But the idea is exactly the same. Okay? The idea is exactly the same. Okay? So the thing that is different is that this perturbation, this big transaction, we'll go back to this later, is that is a special one. That's the key aspect of iterated local search. Okay? So you get initial solution. It could be a heuristic method. So here is, you do a local search. And then you do this perturbation step. And then you do a local search again. And you repeat this until you are tired. And this is the good thing also for this Metaheuristics, is that if I have 5 minutes, I run at 5 minutes. If I have 10 minutes, I run at 10 minutes. Okay? If I have 5 hours, maybe I don't need to run at 5 hours, because the behavior after a certain point, it does not improve. Okay? So for a very simple implementation of iterated local search is that you generate initial solution, so a constructive. You need a local search. So it's the base. You need an acceptance criteria, which is a function which is very simple, which can have different acceptance criteria. And you need this perturbation. And for example, on this perturbation, on the most basic implementation could be one move of a higher level neighborhood. So for example, the TSP, if I use a 2-opt here, a 2-opt, so I remove 2 edges and I put 2 edges. On the perturbation, I do a 4-opt, one move only. Okay? Even I will recommend, usually this is not the best implementation, but with this, we always get very good results. It's simple, it's robust, because I can change it very easily, and it gets very good results in terms of time and in terms of solutions. Okay? But if you want to go to a higher level iterated local search, you can do even a randomized greedy. You can put like a GRASP inside the iterated local search, can do it. You can have different acceptance criterions, like the type of simulating annealing. You have a cooling system, that's perfectly acceptable. You can do even better methods here, not only the local search, but put a taboo search, put a VNS, put whatever type of local search algorithm you want. And then it's the key, okay? You can have really, really a high-level perturbation, even using some optimization, exact optimization here. Okay, this is the key. Constructive, destructive, there has a name, this heuristic, that you destruct part of the solution, then you construct again. I consider, some people say this is not iterated local search, or is, I don't really care about these names. But this is a type of perturbation, because some people understand that the iterated local search was only do a move of high-level neighborhood. No, I've never said this. It says you perturb your solution, and I will go back to this. It's very important the way you perturb your solution, because you should have a relationship between local search and perturbation. So the perturbation should be designed such that you get a solution that is not easy to find with the local search. So using a 2-opt on local search and a 3-opt on perturbation, it's not a very good idea. Because the perturbation should be done that to change the structure of the solution, not the objective function, the structure of the solution in such a way that you will never get there when you do the local search. So this is when the mathematics really, and the structure of the problem really understands, okay? So for example, in one of my applications on Job Shop, what I've done is that, okay, on the perturbation, I forget all the other machines, I relax all the other machines, and now I optimize one machine only. This machine has the perfect schedule, but when you put all together, it's not necessarily the perfect schedule. But the local search could never get such a perfect schedule in one machine. But I optimized this one machine on the middle, and the others were, especially after, were a complete disaster. Okay? So the perturbation should lead to a new region of the solution space that cannot be reached by the local search. And this is an idea, something that if you want to work with me, I've never seen to prove this on the paper of iterated local search. I didn't do it myself, so it's a critic to myself, to prove exactly this. But this is the idea of the perturbation. Really move away, and this, I'm talking about the structure of the solution. I don't care about the objective function. Then on the local search, I will improve the objective function. There's some work on a person, Karen, I don't remember the last name, she was in MIT in Australia. She did a very nice work about the structure of the solutions. And she was, for example, proving, so as we have the P and NP hard for the algorithms, she's proving she has some theory about the structure of the solutions. If some problems are easier than others, why they are easier than others. It's a very interesting work. So the perturbation can and should improve at problem-specific information. For example, as I said, optimization method, destruction construction approach, and it should be a good perturbation transforms one excellent solution, like a local optimal solution, in an excellent starting point for another local search. Okay? Local search must be fast, and complexity must be added progressively in a modular way. So you can start with some simple perturbation and see really if your structure of the solution had changed or not. So if I do recommend that, because many journals, when they iterate local search, send it to me to referee, and sometimes I say, why did you pick this perturbation? That's my question always. So if you get this question, I know I did the referee. So why did you pick this perturbation? Because I think this is good. No, we don't do things like this in science. Okay? Why do you think it's good? So did you really show that this kind, for example, in the TSP, this four-bridge move, that really changes the structure of the solution. It's a good perturbation. I think this is one of the best heuristics which is Thomas Schutzler who did it for the TSP, because they change the structure of the solution. So this will bring really science to your paper, not just implemented one more iterated local search. So just implemented one more iterated local search is becoming not very good accepted in journals. Okay, you have to really justify why your local search can be simple, but the perturbation is the key factor. And that's what it differentiates us for the grasp. The grasp uses the randomness, which is a good idea. Here we use a different strategy. Okay? You can also use randomness in the perturbation, but it should be on this new region of the solution space. Really, the structure should be different. Okay? So this is my Google search. This is my argument to get promoted in the university. So I give you ideas. So this is from the 2000 to 2017, the growing. I think here there's missing some publications because I got this data before, just in January, and sometimes you need time to get this on the Google search, which is more than 8,000 or almost 9,000 publications. Not everyone cites, but that's okay. And as I said, I like iterated local search because of this things it does. So if you look on the literature, it gets very good results for very complex problems, for large scale. You get very fast answers. It can be changed very easily because if the problem changes, maybe you don't have to change the local search. You can just change the perturbation. Okay, I will make this available on the web, the PowerPoints. If for all speakers, if they give me permission, I will. And IBM said they will do it, so I will put them maybe next week or the week follows, but I will put it available. And it's simple. It can be a fast implementation. If I have a local search, I just need to think very well on the perturbation and put all together. And every problem has a constructive heuristic, so it's quite simple to implement it. Okay, so with a little bit of history, I came to realize, because I'm old, that some of the students don't know the history of why these things appear. And yesterday I come with some history, because history is that where you come from and where we want to go, right? So the first paper, why did I work in iterated local search? Why did I start? When I was a PhD, I did my PhD at Cornell University. I have a very theoretical advisor that if I don't bring theorems and proofs, it will think my work is really bad. Okay, not a very good relationship with him. So you see, you're lucky if your advisor is pushing you to do work. And one time he gave me this paper. What do you think about this? And I thought it was a fantastic idea. So this is a paper by Olivier Martin, Steve Otto, Edward Felden. It was Olivier Martin's thesis. He's in physics. Okay, and it was mostly his idea. Okay, it was mostly his idea. So what he's doing, and that's why I think you should read some good old papers. Don't think it's a paper is old, is bad. He read Lynn Kernaghan paper. Lynn Kernaghan paper is the most famous heuristic for the TSP, which is, I think, I don't remember, I have to check, it's really old. And he thought, use this called large step Markov chains for traveling salesman problems. So he's applying his knowledge on Markov chains and say, okay, why don't I understand the search as a Markov chain? Okay, it's brilliant. It's really amazing. The idea was really good, and he got very good results for the TSP. Much better by the. This is 92. By 92, this was the best results for the TSP. Okay, he was in physics. Okay, but he read Lynn Kernaghan, which is an operation research paper. So now sometimes you have to go out of your area too. So we come to this, and I thought, wow, I can apply this to my job shop scheduling, because I'm not getting very good results with the current heuristics that I have. Okay, so I decided. So this is the paper. It's Lynn Kernaghan local search heuristics combines good feature of the local search method with Markov chains to produce more powerful time of Monte Carlo procedure. That's standard simulating annealing. Simulating annealing by the time was the fashion. It was like everyone has to have a simulating annealing. Okay, which is just a local search with that you don't stop at the local optimal, you keep going, and then you're cooling. So at the beginning, you accept every solution. At the end, you just accept if it's a local optimal. Okay, so we did this iterated local search. You did the local search with a 3-op, and they did a random 4 change move and a double bridge. So you see, the perturbation here was already very smart. Was already quite smart, quite designed for this problem. So I think this paper is really fantastic. So I thought the idea was great, and I said, can I do it for my job shop scheduling. So I did it for my job shop scheduling. I applied this. I call it large step optimization methods. It's published in Azure. And I apply it for the job shop. And I mean, I use very basic, very standard, like similar perturbations. Okay? So what I did is I did the priority dispatching rule by Adam Balint. This is a classic for job shop scheduling. You know, for those of you who work in scheduling know this is a classic heuristic. It's basically what they do on reality. It's like getting a rule, first come, first served, and you schedule like this, or you have some rule and you schedule following this rule. And then I did a 2-opt from Lauer, Van Hartz, and Lanstra, and a simulating annealing. But here, this is where I thought it was the contribution. Okay, so the perturbation phase were already what we call today a math heuristic. Because what I did is solve, I picked two random machines, and I solved them one and another one, and like in 2 steps, to the optimality and one machine scheduling problem by Carlier. You have release dates and delivery times, so it's not a one machine scheduling. One machine scheduling is solved in P time, but this is NP complete. Okay, so this is an NP complete. One machine scheduling problem is NP complete. So I used a branch and bound. Carlier and Pimpson was the best branch and bound available at the time to solve this. In reality, Carlier and Pimpson solved. There's an instance from the job shop scheduling, a very famous instance from Wood and Thompson. It was appeared on the literature in '64, and it took 20 years to prove the optimal solution. And they proved the optimal solution for 20 years to prove that the solution for that particular instance was optimal. Okay, so the other day, Daniel Serra, my colleague, he has this book from Wood and Thompson when this instance appears, because it was from his father. His father was economist to have this book, and I was kind of, wow, I mean, I've never seen the book. Now we have this book, this instance is a 10 by 10, 10 jobs on 10 machines. It's a 10 by 10 instance, appears in the literature in '64, and only in the 80s, 85 or something, they could prove the optimal solution. Okay, so you can imagine even 10 by 10, which is kind of amazing. So what I did in the perturbation is solving this to optimality is one machine scheduling problem, and then you could solve the 2 machines, like a 2-machine scheduling problem with an heuristic called an algorithm that I designed myself. Is an exact method to solve these 2 machines. So the structure of the problem was completely different from the solution, sorry. The structure of the solution was completely different from whatever you get if you do the same 2-opt, 3-opt, 4-opt structure, okay? So this is a little bit what I got, what I apply, where I get this idea from Olivier Martin, and this idea is his, and I apply it to job shop scheduling. Okay, so this come out 2 papers on the 95 and 96, where you do this, in reality, we realize on these papers that the local search was very weak for job shop scheduling. The local search, there's so many local optimals that you you finish very, very fast and you get a very bad solution. So the landscape of the solution space is like with a lot of alls. And there's some paper that proves this. So if there is a landscape with a lot of alls, you get to very bad local optimal fast. So you need something else, and then we apply simulating annealing taboo search to improve that, not getting stuck so early. Okay, and this is a little bit the same idea. Okay, so I didn't know the name. I'm not good. So this was an hybrid Metaheuristics, and this was a math Metaheuristics. Okay. So even at that time, there was no names for this. I think even Metaheuristics appeared 93. It was the first conference. 93? 86 when it was called, but the first really conference was 90-something. So 80-something was when Fred Glover is the father and named the area. Okay? So at the time, so this is a hybrid Metaheuristics and this is a math Metaheuristics, okay? Today. Okay. Then and then in later on, Thomas Schutzle, okay, applied this same idea from Olivier Martin to the flow shop. Okay, the same idea to flow shop. So he has also a very famous heuristic for flow shop, and has a score and am. He has an insertion algorithm and swap and exchange for perturbation. So he also read the paper from Olivier Martin. And we all met I met with Thomas first time in '99 in Brazil. I've never met Olivier Martin, even I write a couple of papers with him. I never met him personally. You can imagine now, it's really amazing, this world. But I met him, and that's when we start working on structure, this iterated local search, okay? So networking is important when you go to conferences. Not talk only with your friends, but talk with people that maybe it's not your friends at the time. Okay, so we have a lot of names. We start with large step Markov chains, iterated local search, chain local optimization, iterated descendant, iterated Lin-Kernighan, local search with perturbation, iterated greedy algorithm. I don't care about the names. I care about the structure, okay? So I even have one time a referee telling me it was an iterated local search and say, this is not an iterated local search. This is some of these names. I say, okay, whatever you want. If you want, I call it Pepe, Maria, and if you get published, I find these comments really, really absurd because this is not science. No, this not contributes to the science, putting a name or saying that this is not this name, okay? But working later, you see that, okay, so Lin-Kernighan, as I said, was 73. There's some other work before we start working that we knew it after, that they didn't call none of these names, but when you look at the structure of the heuristic, is it the same structure? Okay, they just call it heuristics, no name. Okay, so this is a little bit of the history, and of course, it's, as I said, it's my favorite algorithm, and it's the one been applied for many other applications. Okay, let's go to the traveling salesman problem, which is quite simple. I've never applied it to the travel salesman problem. This is more Thomas Schutzle is the one who have applied it. Some other researchers, but I've never applied it. So this, all of you know the problem. We have a number of cities. You have the distance between every city, and you have to go to find the round trip among all these cities. I do recommend this web page. I use it a lot for my students because they have a game. So I bring them on the, if I have time, maybe I can do it. Sometimes you need a Java script. I don't know if the computer has it, but I have a game and they have to come to the computer, do the game, and no one gets never even close to the optimal solution. And then I show them, how difficult these problems are. So I usually teach turnaround. I put them the problem. So first day in the class, I give them a problem. They have 1 hour to solve it. They can call everyone, look in internet, do whatever they want. It's a routing problem. It's 20 malls in Barcelona. They have to decide this distribution, and they say in 1 hour the trucks must leave. It's up to you. I hire the best. And no one gets even close to the optimal. Not even the Clark and Wright solution. I don't give them the data. That's another lesson, okay? I can share with you this thing. So, for example, for the travel salesman problem, so things that people have been done. So for the TSP, construct heuristic, we have nearest neighbor, which is usually not very good, insertion heuristic. So we have lots of heuristics. There's this fantastic book from Leinster that you have lots of heuristics. You can do 2-opt and 3-opt. The perturbation, you can do double breach. It's a 4-opt double breach. So it's a special type of 4-opt. As I mentioned, the perturbation should not be, in most of the cases, unless you want a fast implementation. I want a fast implementation, you can do 2-opt, and then 1 move of 3-opt in perturbation. That's it. If the company pays for that, fantastic. But for research tools, the perturbation should be a higher level, something more elaborated. And also this idea, go to another region of the solution space. that. So look at the structure of the solution. And then accept only if it's the best. So this is a very simple implementation. For the max cut click, I explained this problem yesterday. This was an application in marketing. This problem was completely new. I don't think there is, except Pedro Martin, who was the one who, we have these big databases in marketing, and he has this idea about this problem, and I talked with the marketing people, and we thought it would be interesting for marketing because, as I said yesterday, if you influence these two guys, you are influencing a lot of people. So in marketing and social media like Facebook, you are looking a lot for the centrality, the person that has the bigger influencer. But here you have, because if you influence these two, they talk, because they are connected, so it influences everyone. So this is the max cut click. So I want a click that has more connections going outside. Okay, so if you see, this is the maximum cardinality click. This click has 4 elements, 1, 2, 3, 4. Everyone is connected. Here you have a click with 3 elements. Everyone is connected. But this one only has 2 external connections. Okay, so the perturbation was you select a random node, and then you reconstruct the click from this random node. So you select a random node from the previous click, and you construct the click from this random node. And local optimization is very simple. You swap and do aspiration moves. It's quite tricky because, of course, if I say swap this from this, these two are not a click. So I cannot just swap like in many other problems. I need to swap in a way that I still maintain the click structure of the solution. Okay? And here are the solutions, a little bit. So we have the mathematical model. We run in Cplex, 11.2 at the moment. At the moment, we run it for 1 hour. So this is the data. This is a typical toy problems that I mentioned before, that you have to do this for published most of the time. You have the maximum cardinality click, so you can get the optimal for the maximum cardinality click for all except this one. But for the maximum cut click, for the largest instance, we cannot get the optimal in 1 hour. Okay, we cannot get the optimal in 1 hour. We can get here, but not here. Okay, so which is more difficult than the maximum cardinality click in practice, not in theory. Both are NP hard. Okay, when you get the iterated local search that I mentioned before, so we get all the optimal in much less time. So you see the time, look at the time here, look at the time here. And so the time is reduced significantly. And of course, this one, we are very close to the optimal. I think it's 2% or something like that. Okay? So this is an application on the click problem that I mentioned before. So we apply this to the market basket analysis. I mentioned this, so I won't repeat very fast. It's just market basket analysis, what you put on the basket when you go shopping, special supermarket. Okay? And this is very much applied for personalized campaigns, marketing campaigns. So you go to the supermarket and you put orange juice, milk, and this is a basket. And they register that. And it's really surprising. Some supermarkets have this fidelity card that you use at the end, so they know exactly what you buy, and they just use it to make you discounts. What they could do with that data is amazing, because they know exactly when you buy, what you buy, everything. So, for example, I have this example that I will give. I have a supermarket that still send me every year by this period, by maybe March, April, that's when more babies are born. That's true, huh? They send me every year like a campaign about newborns and babies until 3 years old. I mean, didn't you realize that for the last 10 years, I didn't buy any product for babies? See, my kids are already big. I say, why it's a very expensive catalog, a lot of money, and what do I do? Goes directly to the garbage. Or recycle garbage. But why they spend money on that? See, they can know everything, but you know what they do? There's one supermarket, they say, oh, we delete them because we don't have space to store all this data. Can you give me this data, please? No, they can't. Okay. So this is very interesting for marketing, for product placement. So think about a supermarket. When you put the products, it's very important. So I don't know if you know that the companies, the manufacturers pay for the space. So a supermarket does not only make money what they sell, but make money with space. So the best space is this. I'm average weight, okay? So I'm here. Here, oh, I have to go. On there, I cannot get there. The corners, and this, so you see the promotions are on the corners, and this is the best place. So if you want to see the best brands are at this high, okay? So, but what you put together? Yes, you have to classify by pasta, but what kind of pastas you put together? What kind of yogurts you put together? Because you can say, oh, I'm going to buy spaghetti, and then say, oh, looks nice, this thing. I'm going to get it too. Because I got the spaghetti and look around, there was something that, you know, a new product, something. So its placement so this helps this, optimal product line offering, personalized marketing campaigns, product production. So here the nodes are the products, and so far we have the links if the product was in the same basket up to a certain number. So here we're not putting weights. That's the next work we're going to do. We don't put weights. It's just up to, if you 100 persons put these products on the basket, there's a threshold, you have this link, okay? And this is our results for this. So this is the maximum cardinality, which you see if I do campaign on this, the impact is smaller. But here you can see it very visually. So this is visual data. You see it very much the impact that I have. I have few number of products that I have to do campaign, and the impact is much bigger. Okay, we did this. Oh, I don't have. We did this for ice creams. It's a product of ice creams in UK that we did this work. I thought I had the thing. I'm going to jump this because this I don't want to do. Okay, so this is the main references in iterated local search, 2003, 2010, and there is one coming, I think, this year, 2018. Okay, this is the three authors. I'm the first because my last name. So my story of my last name is complicated. So just check my web. It's not because I'm married twice. It's because in Portugal we have a lot of last names, and we can use any you want. You can have up to 6 last names, okay? And you can use any you want. And in Spain, in Spain they only consider the first last name, so they never realized my last name was Lorenzo. And one time the director come to me and say, "You don't have any publications. It's really terrible. I don't think you deserve a promotion." Said, "Oh, come on, I don't have any publication? No, please." And then I decided that I switch names. And also because of this, the C, no one could. I have a list of papers that cite me incorrectly. A lot of papers that don't cite me. They call me Lawrence, Lorenco, whatever. So I decided to change my name, but it's a long story. You can have. I even have the link on the Portuguese rule to put names, okay, which is completely different from Spain and from other countries. Okay, so this is a little bit the introduction to iterated local search, and now let's go to the extensions. What work we are doing together with the Angel Juan, which are over there hiding on the back, and some other people on extension this iterated local search. And I did this cloud computing from your book, huh, Christian? This is, look, which is the word that appears more?
It's from a journal paper.
Yeah, it's from a journal paper, yes, that's true. Look at this. Okay? So this is a nice thing. I got your paper, I put it in the cloud and say, look, solution. And that's exactly what we do. We provide solutions, good solutions. Okay, so I like it very much. So iterated local search, SIP iterated math, iterated local search. So the ideas that I mentioned is that it's easy to implement, to adapt iterated local search. But real problems are complex, And also there is some stochasticity and uncertain. That's uncertain data. We have to deal with uncertain data. Many people deal with uncertain data, the theoretical people, with the average. You go to the companies and talk about the average, they don't like it. What they want is robust solutions that in case there is changes, the solution is still good. And this is a different concept of optimality. Okay? So let's see how to integrate all these kind of things. So hybrid, iterated local search with others. I already mentioned that my first implementation in LES was an hybrid. So you can hybrid with everything you want. Even you can hybrid with any of these or your favorite even genetic algorithms. You can hybrid with this. Or you can do in the perturbation, do large neighborhood changes. Even some similar like a VNS, you can do this. Okay? So this is an hybrid. And we use this, for example, to solve a real problem here. It's from Gisona. So those from here, you know the store probably. So they have 400 stores. 400 stores. And they deliver every day. And they have a lot of constraints. So a big truck cannot go to the center of city. So for the old part of Barcelona, you cannot send a big truck. You have time windows, okay? Because the stores want to be delivered during a certain time. You have constraints on assigning some trucks to stores. You have time windows. We have maximum driving hours. I cannot have a driver like 10 hours. You have multi-trips. So for stores that are located close to the warehouse is in Gisona, which is in the center of Barcelona. So the warehouses is the center, so you can load, unload, load, and unload the same day. We have sales constraints. You have 7 different types of trucks. You want to minimize the cost. We have the cost. Here we have a cost. It's a very complex cost because it's not only the travel distance, but it's also they pay a cost if the truck is not full. They want to sell the truck always full. Okay? So we use this algorithm, which is, you see, is a hybrid. We use a grasp to get initial solution, local improvement by variable neighborhood descendant, and then a perturbation is a random neighborhood really specialized for this problem. Okay? The results, I can only show you a couple of instances from the company. Okay? And we could improve about 10%. Since we are taping, I cannot tell you the value. But if you ask me on the break, I can tell you how much money it is. Okay? Because if then you say, you said this, I say, no, you're wrong. You just misunderstand me. Because I cannot disclose some information. But you see, it's really an impact on the company. It has really an impact on the company. Okay? Okay? So it's about 10% savings respect to actual solution. They have a professional software. They got a professional software, but they were, so this is a company, for those of you who are not from here, it's companies like Inditex, like Amazon, like Dell, like Gisona, are companies that are innovating on the management. So they're doing things on a different ways. I'm lucky to be in a business school, so I get to learn these kinds of things. Are original. Their management is completely original. Okay? It's not the product per se. So we don't buy a Dell computer because it's much better than anyone or because it's different, like Apple. No, Apple is like a different thing than all Windows. So it's because the management, the way it created, it's completely different. And innovating in management is much better than innovating in product, which is every time I see this innovation, you think about new product, right? New car, no. Innovation in management, because innovation in management is much more difficult to copy. Why we don't have a lot of IKEAs? Why we don't have one IKEA? So when you want to buy furniture, what is the first company that appears in your mind? IKEA, right? And then, okay, I want something better quality, like with real, wood or something. Then you start thinking on other ones, okay? So companies that innovate in management are leading for many years, okay? And they stop leading usually when they stop to innovate it. Also, you can innovate in product like Apple. Apple is an innovation on product, but also in management, because what they did in retailing in their stores is completely original. So you can go to the Apple store and get this service. No other company is offering this yet. So you see, but this innovation in management is really the breakthrough and really makes the company to lead for many, many years, because it's not easy to copy. It's very difficult to copy. So Gizona is a company that innovated in management. Yes, the CEO of Gizona is really an outstanding person. He's like an Amancio Ortega on this area. The thing is that, of course, it's a food company. Food companies are not multinationals, usually. Supermarkets, I mean, is meat. So it was mostly start with meat. So this is not, but it's still very innovative company, very open to new ideas. Then, because the referee said, oh, you have to compare with other algorithms, but then no one have studied this problem. How can I compare to other algorithms? This algorithm is designed for this problem. I mean, but they insist, and we said, okay, we turn around the algorithm, change things, and we can compare it to Prince's algorithm, which is a very good. There's a simple version of this problem, which is a very good researcher, and we get 2%. So, okay, you can publish. It doesn't matter, you save 10% of the company. So another result of this, you need less vehicles. They really like that, because they need less vehicles. And we could contribute to the collaboration between sales department and the logistics department. Because this company, so as a different, the stores don't place orders. The company said how much you send to each store. They can change the orders. So the company said, I need this quantity of chicken, but I can change it. Okay? And this is a very important thing for the business, because that depends on the stock. If they have a lot of stock, they can send more product to the stores. And this is meat, so the due date is very short. So if you have less time doing the routing, you can spend more time doing this kind of analysis. And they like it very much, this. They could not quantify this. Okay, so this is a real case that we have done. Then we have simulation iterated local search. So this is a work that we've done, and it builds on a talk that we're going to have today, right? On Metaheuristics. So Angel will explain very much the Metaheuristics, which is, I think, is a very great idea, because many data today is stochastic. And we have to make a decision before we know exactly what's going to happen. In business, this is amazing. So here I'm going to explain very briefly the SimELS, which is combining these two. There's several techniques. It's not new to the simulation optimization. Fred Glover have done some work. Of course, Fred Glover have done everything. I mean, every time you think you have a new idea, you look and, oh, okay, he did this idea 10 years ago. So, but these are some techniques here on combining this. I'm going to present this. The idea is that, okay, you have a mathematical stochastic model. You turn it into deterministic. You solve it with LES, you do simulation, and you go around this. So the idea here sometimes is not to get the optimal solution turning on average data, because on average data, it's not good. So think about service levels. In companies, service levels are between 95 to 98%. So this means when you go to the supermarket, so think about, you go to the supermarket and you only find 50% of the products that you like. You will repeat? No. Never. You go to buy clothes. They only find 50% what you're looking for. No, you don't repeat. So the service levels are much higher. But then if you plan for 98%, you spend a lot of money. So you need to have this. It's very tricky. Okay? So what we propose together with several people, including Angel, is, okay, again, simplicity. Be simple. That's my main thing. So you get the local search, but you do a very short simulation here, Monte Carlo simulation, how good my solution is. So I optimize, I do local search with deterministic, but I look at this. And then you do the perturbation local search with deterministic and look at this. The idea is that you get this statistics can be included on the perturbation. Okay? This statistic can be included on the perturbation. For example, if my demand is stochastic, I do the average, I get the average, and then here on the simulation, I realize I don't have enough vehicles to satisfy in 95% of the days. I cannot satisfy my demand because my capacity. So maybe I should, change, not using the average, but using some more data. But maybe in some cases I don't need to increase the data. So this statistic gives me insights. How should I touch the data, for example, to run on the next deterministic algorithm? Okay? So the idea is looking at again of the scheme of the local optimal is that you have different curves because your data is stochastic. So you have different curves. And you don't want just the best of all. You want the best for many of these curves. So for example, the best for the green should be somewhere here. Okay, but then it's quite far away in this scenario. So you need to really use, it's like running with different data so you can get the best solution for in a certain surface level. So for example, if the solution, the objective is a stochastic function, okay? So you always maintain the best stochastic function. You always compare to the best stochastic functions in many, many simulations. So we use simulation to detect how good your solution in real cases. And then you change the data or change the acceptance to be able to get a solution that is robust in a certain level, okay? Or for example, in case of stochastic constraints, you have usually what they call the service level. The service level, so how many orders I can deliver if I do this route, okay? How many orders I can deliver if I do these routes. And just for service, you put here the service levels in 98%. If it's not, you have to change the data, to do this. So you run the optimization, deterministic simulation. So simulation should be fast, should be like a Monte Carlo, very fast. And at the end, you can even run a long simulation to see how really this solution is performing. Okay? So remember, simulation does not optimize. Simulation looks at what happens in real life, okay? But applications, as I said, Angel will talk more about this, is the specialist on this, is one who knows much more than myself, so it's some on Flowshop with stochastic processing times, and this has got very good results, and I think here you have another work from Angel, inventory routing problem, and I think you have some new papers already, right? Okay, so I will leave this to him. We use this also on a real case, which is home care planning. This is a work done with Federico Malucelli and Marta, which is his master student. And here it's to have medical attention at home, and it's quite a very important issue today. We're trying to do this in the Barcelona city. Okay. What happens here? What is the problem? It's a VRP, but we have VRP, but it's not exactly VRP because the nurses have some specialization, so they can go to some patients and not. You do a 1 week planning, and you can also assign which day the patient is going to be visited. For example, some patients say, you have to visit once a week. I can decide if it's Monday, Tuesday, Wednesday, Thursday, or Friday. I can decide this so I can balance the capacity better. And also, for example, I can say a patient must be visited twice a week and with 2 days in between. So I can put Monday and Thursday or Tuesday and Friday. Okay, even Saturday and Sunday they also have. So this is a very collaboration with the doctors. The doctors have to decide the data. this is work in progress. Oh. Okay, so we have similar, we have only preliminary results, and moreover, it's a multi-objective because we have costs, but we also have service level. Okay, I cannot assign like a nurse be working 9 hours every day, and another nurse is working 5 hours every day. We're going to have a problem here. And this is not a cost. This is a balanced routes and et cetera. So this is the work that we are doing with this stochastic and using SimELES, which is, let's say, an extension. It's multi-objective with simulation and ELES. So we put everything together. The bias randomization heuristics, I will skip this because he is doing bias randomization because Angel is going to have a talk tomorrow on this. So I will skip this, but it's another extension that we are working that using some bias when you do decisions on the ELES. Okay, so we use some bias and not just get like a uniform random number. This I will give this to Angel. And this is a work that we have done many years ago, but he has also some new ideas on using this biorandomization. And I'm going to skip this, which is so you have a bias random over there, and you can have a bias here. Okay, so this includes randomization in the ELES, and it gets quite good results. We're not calling a new name, huh? Okay? It's just saying that it's mixing what other people are doing and getting this good idea to put it together in these ones, okay? So you can use this bias in the 3 steps of the ELES. Right? So if I'm come here, they don't, okay. So the last one is the Metaheuristics. So Metaheuristics is, as I said, I implemented in my thesis, which I didn't call a Metaheuristics, which I should. It's a good name. I like the name. So it's putting together these 2 worlds, okay? Putting together the 2 worlds. I hate when they discuss which you are theoretical, you're not theoretical. I hate this because I think these are tools, and we should have to use the best tools possible to solve the problem, okay? So we have the local search, you have all this iterated, these exact methods, branch and bound, branch and cut, column generation, cutting and price, dynamic programming, Lagrangian regularization, linear regularization, zero-gate regularization, whatever. You have this, and the idea is to get the good things of both worlds. Okay. What are good from local search Metaheuristics? You can solve large-scale problems and complex problems in fast time and are easy to adapt, as all we mentioned before, but we don't have a proof that it gets the optimal solution, or even how close we are to the optimal solution. Every year there appears a paper that tried to prove things like this, and I think it will never be it was never published because it was mostly bad. I don't know if Christian is more an editor. I've never seen nothing that was really serious about, yeah, in the limit, the simulating annealing will get the optimal. What do you mean in the limit? I mean, running forever, the algorithm? Yes, but are not practical, okay? So, and also, a thing that I like about exact methods is that they use characteristics, mathematical properties, to obtain good results. And why are not we using mathematical properties to get results in the Metaheuristics? Why you have always to do random, which is good, but maybe, and that's the idea of the Metaheuristics, using these mathematical properties to really speed up the search. Okay, so exploiting the mathematical programming techniques, grading the mathematical programming approach to cross-problem robustness and constraint, and really be effective, very efficient on doing this Metaheuristics. For me, on the iterated local search, this goes on the perturbation. And this is what I did with my thesis, and I think I like when I see people doing this, because this is what goes on the perturbation. Local search must be fast. You must just go down very fast. But here, we can do a little bit more. Maybe take more time here, but overall, you have less time. Okay, so this is the smart idea to using this here. Okay, so this is what I've done in this paper that is published in '95, and then I improved them in a work that I've done with one of my master students in 96. You're using this solving to optimality one machine scheduling problem then inside the job shop scheduling problem. Or for example, if you use vehicle routing, if it's route as 20 customers, you can apply a Concord. Solving a TSP for 20 things today, it's really fast. So we don't need to do moves inside the route because we can solve it very fast with the computers. Okay? Of course, that we still have the decision if that customer should be in that route, but then we do it on the local search. We deal with this on the local search thing, okay? So it's a little bit the idea here. I've never used it, but I think there's someone who's done this using, for example, dynamic programming also. So the idea is to bring these good ideas, good characteristics of the problem, mathematical problems inside the metaheuristics. And I think this is a really, real idea. And for real problems, this is even better. Because real problems, and I mentioned this yesterday, are problems that we kind of know, but more difficult, more complex, more constraints. Is a vehicle routing with time windows with different vehicles that, you know, the customers need this, the customers did that, and this kind of this. But we can go back to the vehicle routing at a certain point, and we complicate it because it's real life, it's complicated. So we can use everything we know about theory about vehicle routing on the perturbation or relax. So in the perturbation, we solve a relaxed problem of the real problem. And on the local search, we put every complicated thing of the real problem. So I like this kind of problems because the kind of ideas, because sometimes I see a real problem and it looks like the researcher is doing everything from scratch. I mean, don't you look at the literature and good things that you've done for the TSP, for the vehicle routing, for the location? I mean, there's a lot of theory behind that. We should use it in a methaheuristic and speed up the algorithm. Okay? Of course, that's what I mentioned here. Exact methods to well-known relaxation of the problem. A small instance, you reduce the small instance, you do okay. So I split my problem in regions. And I solved to optimality this. So for example, or I solved to optimality this part because it's a set covering, but it's a very small set covering. I can solve this to optimality. Of course, this is sub-optimization. If I optimize this part, does not mean that the overall is optimal. Everyone knows that. But I can, you know, solve this very fast. Okay? And this changes the structure of the solution. The perturbation is always that, changing the structure of the solution. And this does change the structure of the solution. My experience that with local search, if you optimize like a relaxation of a sub-problem, with local search, we never get to that solution. Never. Okay? Well, and also something that I'm working is in bi-level optimization, okay, using this kind of problems that we have two decisions. I have to locate my warehouses, and then I have the routing. The routing decision depends on the location. If I do a bad decision on location, I do a bad decision on routing. Okay, so this is very strategical. I wanted to go for very strategical decision problems because the money is on strategy, not on the operationals for business. Okay? So here it's usually is a neighborhood. We can do both things. Good the neighborhood on operational variables. You do the optimization strategical decision. For example, location. Okay. We can locate, and then you can assign the customers to the location. For example, if you have no capacity, this is if a customer can be served by more than one warehouse, this is a transportation problem. If not, it's a generalized assignment problem, and that also can be solved quite easily. Okay, and you can do it the other way around. So that's a decision that when you design the algorithm to see where you should put the operational variables and the decision and the strategical decisions and which part should optimize which, okay? So this was done in a work that we published recently. It's a two-stage stochastic programming problem. So it's stochastic, but this is for e-commerce. So e-commerce, they have to, for example, to take an example, Zara has 2 warehouses in the world for every store. One in Arteixo, one in Zaragoza. every order for every store in Zara comes out to one of these warehouses, even if you are in Melbourne. Okay? But for e-commerce, that's why Inditex took so much time to enter e-commerce. This is not true. They need to have more warehouses. Because if I'm in Melbourne and I order, I want a 24 hours delivery. Even now, they have less than 24 hours. So if you buy in Massimo Dutti, in Barcelona, they can deliver in 3 hours to you. Okay? Which is a lot of pressure. Maybe if you are like in the middle of Catalonia, no, but in the big cities, yes. So they cannot have the warehouse. If you order in Melbourne and have a warehouse, have the small order, my shoes delivered from the warehouse in Zaragoza. This will be very, very expensive. So they need to have more warehouses. And another important thing is that they cannot have every product in every warehouse. Because how many products you have in a store like Zara or like El Corte Inglés? So my students, I ask them to go to a store and count how many different products they are. Not products, what we call SKUs. Is spaghettis, you can find spaghettis in different sizes. Half a kilo, okay? So each of these has to have as a reference number. So how many of these references numbers exist? And they get tired to counting, especially El Corte Inglés. Okay? So they need to have, but they need to know, and that's something that Amazon is also doing, it is, I order in Barcelona, which warehouse is serving me? So in all warehouses that serve, for example, Barcelona, all together, they should have all the products. Okay? So you can have more than one house assignment, which is in normal retailing, they don't do it. Okay, so here we use a local search to open close warehouses and an exact method to assign the demand on different simulated scenarios. So assigning demand to a warehouse is a transportation problem or generalized assignment problem. Generalized assignment problem is NP complete, but it's solved very fast in any this because it's NP complete, but it's easy in practice. Okay? And we also compare this with some theory on deterministic equivalent model, which is this. Okay, deterministic equivalent model is when you optimize for every scenario, create many, many different scenarios. Adela Pages, who's seeing me on streaming, hi Adela, is a specialist on this. This is the theory behind this, and we compare with this. This is like what people use in theory to solve this problem. Then you see, okay, we could, with the stochastic programming, we could only solve the small instances. With the big instance, we have to go to this, and with the large, so we have here about 1 hour, and here we have, even we don't get some good solutions on this technique, but we can solve a largest one. We still need to work a little bit, but okay. Okay, so I think we are also working on this, Metaheuristics, putting this equivalent deterministic model inside the Metaheuristics, again, on the perturbation. So the math part always goes on the perturbation. Okay, and other extensions is with the Martin Gomes-Rabete, we are using Lagrange generalization iterated local search. You can use Lagrange generalization using ELES to obtain the lower bounds, to force the lower bounds to be better. Multi-objective, parallel, ELES, so these are some of the extensions that you can find at this. So which is the best Metaheristic? I said I explained iterate local search and people explain some others. I don't know. I think if you can evaluate it with this characteristic and it's good, it's good. What I said is I don't like these weird names. I don't like these stupid ideas. I'm sorry to say it. I shouldn't say it when I'm typing. About putting names weird and then reinventing things that have been invented, making things complicated so it looks I'm smarter because I have a lot of complicated things on the paper. And I think if you're serious and you can justify the application of your Metaheuristics. My best friend is, my really best friend for many years is Mauricio Rezende. He is a fanatic from GRASP. And, I think his idea is fantastic. Maybe when I come to my mouth, I think about ELES, but why not using GRASP or others? So I think there's people that really make a difference. And with heuristics, I mean, make it simple and efficient. Make it that it gets really simplicity is important. Flexibility is important, that you can, that's our advantage from a branch and bound. So you have a TSP. The best branch and bound in the world, branch and cut in the world is Concord. No one wins Concord. You can download it on the, every time I go to business, I say, this is the best algorithm and it's free. Yes, it's the best algorithm. 30 years of research. 30 years of research of many, many smart people. Many, many smart people. But now I said, okay, I want a TSP, but with time windows. It doesn't work. So this is our advantage as a Metaheuristics. And I think incorporating knowledge from what previous researchers have done and even mathematics will help to really improve the Metaheuristics. Okay, so start simple and add complexity. So you should start simple and you say, okay, if it's for consulting and if company is happy, that's it. But for research, you have to, if you don't get good results, you shouldn't then add complexity step by step. Okay, and now it's almost 9,000 publications, and I will finish. Do you want to try implement an alias? And I'm okay. So we'll have 20 minutes for questions. Was my I forgot about this. Okay. So thank you. Oh, we have a microphone. Yeah. No.
This means Angela and me can go home, right? No.
No, if you can go home, and no. You have a lot of new ideas, a lot of things that I don't know, and I don't know the rest of the class, but I certainly want to hear from you, okay? Because, I just mentioned that you can put hybrid in the LES, but there's a lot of other hybrid and a lot of bias randomization, a lot of heuristics that I really, and I think this is areas that we should promote them more, because it's really, to be honest, and I'm always honest, sometimes I get in trouble because of that. I like that ideas, and I hate when they come with the new fly elephants and even more stupid ones. That's hurting a lot the area. I think our area should go in two directions, on that directions that you mentioned, and more applications. Make ourselves essential for business. Business, I want my dream, and I still dream, even I'm older, is to have like machine learning. People say, I want to apply machine learning. They apply statistics as I learn in my university. But now they call it machine learning, which is kind of, oh my God, I say this in. But
just to add something to your comment about flying elephants. So, yeah. Okay. I mean, you know that there's a strong movement now in the Metaheuristics community against these flying elephants, wolf packs, and whatever they are called, no? Because most of these things are reinventing the wheel or are sometimes even nonsense, no? And for example, in computers and operations research, where I'm area editor since 2 years for all metaheuristics and heuristic stuff, in this time at least, we have not published anything more about this kind of things. I know that Journal of Heuristics has started with this policy, so they are already since 3 or 4 years not publishing anything on that. And I think people start to understand that and stop with these kind of developments. I think I have this impression. I don't know if you have the same impression, but I think it's going down.
yeah, I think it's going down, and I think it's also important to maintain the message.
Yeah.
Because we are a multidisciplinary area. I'm a mathematician. You are for computer science. I think I'm a mathematician, so we have computer science, we have mathematicians, we have physics, and it's normal that sometimes when you come from my age, we don't know what the other area have done. This is normal. I mean, this is completely acceptable. What I think is that when you are a PhD student, you should learn. And if you're going on this Metaheuristics, you should learn about the background and what has been done. And my criticism is that there's so much pressure on publish from all of us, including myself, that's all publish, that we don't give time to the students to embed the knowledge, to get the knowledge really deeply. We pass all the pressure, and I'm from the slow movement, no slow food, but now slow research. That's a good. I like that. That's a new term. So I get I will get credit from this. The slow research. You have to really embed this. And of course, if I'm a PhD student, then to get the job, I need to publish. What I will do, I will publish. I mean, it's all the ones are the senior ones that we should try, and editors too, try to slow down a little bit this. Not the youngest, because the youngest have, they do what we recommended to do, what the society, because the research society. So I do, and I'm going to tell you a story about Mauricio Rezende. I visited, now he's in Amazon, but he was in AT&T. And I visited him several years ago. We went to Bell Labs. Bell Labs, for all of us, is like, wow, Bell Labs, invented so many things. And they have this small museum on Bell Labs. And Mauricio says to me something that I always remember, is that all of this today was not invented, would not be possible invented, because these guys took 5 years. 5 years to get this. And this guy took 4 years. And these guys, we were researching in something and then find out this, and then they, after 3 years researching in something, I don't remember exactly, and then they find out this was something else was working. They try to apply it in another area, now it's successful. So we have to really, as editors, as advisors, the seniors, have to transmit that, try that the student incorporate the knowledge as done, and then it will, not just, paper. But I understand if you do paper. I understand, because then it goes to another job and say, how many papers you have? I go to a project, how many papers you have? And it's like, I don't know how to stop this wheel.
This publication pressure gets every time more extreme. I mean, here in Spain, in the evaluation agencies or the state, right? Nowadays, nearly only Q1 publications in Q1 journals count, okay? Not even journals published, they appear in the journal citation report. No, they have to be in the first quartile, Q1 journals, right? Others start not to count, basically. And this is a very dangerous direction to go, I think. But I don't know how to change that, to be honest. I don't know.
But I agree with you. So how do we change it? I don't know. I don't know. And in Metaheuristics, this is dangerous because, I mean, it's easy to, and I've done it. Huh? You have to implement one more heuristic. I've done it. I mean, so I'm the first one to put myself in this. So I'm criticizing myself. But we need to have some work on more profound work. I mean, that's my opinion. But as I said, for youngers, you do whatever is best for you. Huh? Don't listen to Christian and myself. I mean, if you have to publish, you publish. That's it, okay? So, but maybe you will become, you are our future, so you are the ones who will continue this work or not. So at least try to do it better than we did it, I think. But I agree with you, it's counting. But I must say there is some hope, because there is the doctors, the medical doctors, there's one called the San Francisco Declaration. This is a Nobel Prize, a woman that won the Nobel Prize. And she refuses to go on these things. And she's done already, just starting in the United States, they're already starting this movement about publish, publish, publish. So there is this special the doctor, San Francisco Declaration, because why in the doctor, why in medicine? Because that has an impact, okay? There's really impact on the life of people. So the San Francisco Declaration, if you look on the web, good San Francisco Declaration, they're already starting this movement. There's this woman, this Nobel Prize, the day before she won the Nobel Prize, they get given to her. She make a big letter on the New York Times and some important journals against these things. But in Spain, we'll still, so we come from no research. So some of the oldest professors, no research to, so it's a balance. The moment will come here. And then I got in troubles always, because this will be available. The politicians don't look at this. Questions, more questions. So you see the seniors are giving an example of asking questions.
Helena, thank you for your presentation. I would like to know your opinion about the future of Metaheuristics. So which areas do you think are the most promising ones in terms of social impact from Metaheuristics knowledge? And as well as some recommendation to the young researchers we have here with us, so that you can give us, or give them.
Okay, that's a difficult question. Okay, so I'll start with the first one. Which areas? I think we should go more and more to real applications. So really, I propose this grado thesis, this thesis that my students have to do when they do undergrad. One, to study the impact of the Metaheuristics in business. Get all the papers that are published, for example, in Interfaces, and say, oh, in this business, the impact, the savings was $1 million. And also do a survey. We are trying to, with the Euro and with the SEO, do a survey that you have a business applications, what was the impact? And business only understand one language. Is or you improve the service and the product, the customer service, or improve the costs. Okay? So I think we should go for more business applications. They are challenging. They are much challenging. And they are what we should change, and this is for the editors of the journals, to publish more business applications. Don't ask like this paper that I have with Ari de Gisona, they say, oh, you didn't compare with anyone. And they said, look, I look at the literature, there was no vehicle routing like this, or what do you want me to do? So yes, then I did a comparison, but is that science? So I did this, that really contributes to the knowledge, because I contribute to a simple problem and I could prove it was a simple, but that's not science for me. So we should have more real applications, but the editors of the journal should say, okay, if it's a well-written paper, it makes sense and improves the solution, I want to make publicity on this. Okay? So that's another way. And then go on more this Metaheuristics simulation, hybrid. I think this is, it's really bringing knowledge from different areas and create new knowledge, which is what we do. We create new knowledge, right? So I think these two areas could be the areas. Advices for the students. Oh, I'm not a very good advisor. I mean, work hard, very hard. Some people think the PhD, it's a piece of cake. No, 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 no. All of us who are older, we know we work very hard. Look at what has been done in the past. Okay? Don't just, I have this brilliant idea, like this paper on computer science. Oh, I invented this. They call it, I don't remember now, and it was local search. It was pure local searches. Come on, I mean, it's like, so work hard. And also reach different networks. Okay, so you are the advisor, should be your reference, but ask your advisor to reach other areas. And you should differentiate your PhD thesis. Why my PhD thesis is different from my colleague over there? What I'm really contributing to the society or to the knowledge? How I would like to be remembered in 5 years for my work. okay? Is my work really, so for example, in iterated local search, in many conferences, they think, oh, it was Olivier Martin who created only physics. Some people it was Thomas Schutzler because he was traveling more than myself because I could not travel during some time. Some people think it's me. No, it was a discussion, and the knowledge was done because we discussed. And I don't know how much part is myself or Thomas or Olivier. I know that Olivier was the first to publish that famous paper. So if I have to put the father of the algorithm is Olivier Martin. But this creates something that is different. So what is my thesis different from my work of my advisor? Even it's my advisor, I will build on, but why is different? Why is different my work? What does it contribute to the knowledge? Why I would like to be remembered? But since we don't have time to answer these questions because we have to publish, and I myself have to publish, I don't know it. That's what I think. So no questions. There is a nice. Oh, there's a question here.
I was wondering, when you do perturbations, when do you draw the line when it's part of your local search and when it's really giving you a new subspace of your solution space? So how do you differentiate between just giving a small perturbation to
local search?
Yeah.
Okay, so if you go, for example, for the perturbation is one change on the solution. You change you change the solution in a certain way. You don't optimize. Local search, you try to optimize, to get the better. So, for example, on the TSP, imagine the TSP. So the TSP, you can, for example, you remove 5 edges, to say something, and you reconstruct in a random way. Reconstruct the tour in a random way. So in the perturbation objective, it's not to optimize, it's to change the structure of the solution. And then you optimize on the local search. Local search, you search for better solutions. Do I make myself clear? Yeah. Okay, so there's a nice coffee breakout. Oh, question? Fantastic. You see, it's always the first one who has to start.
So why is this perturbation preserving the property of being maximal? How do you check that?
Okay. So the perturbation, you don't change everything. So, for example, think about the TSP, because TSP is a very didactical example. Okay, so if you have already a good solution, you can remove like certain 5 edges, but the rest of the solution is still good. Okay? So it's not, so from restart, for the multi-start, you start from scratch. Here you still think about, for example, if you have a TSP and you have a certain number of nodes that are very close to each other, it's normal that you visit them in a row. We don't go, I don't do a TSP going from, for example, if I'm doing a tour in Spain, I don't go Barcelona, Bilbao, Bilbao, Sevilla, Sevilla, Victoria, Victoria, Huesca. No, it doesn't make sense that, some structure's still good. The thing is that you want to change the structure, not completely. Okay, so if you remove some links, the rest is still good. So the local search will be faster to find another one. Do I make myself clear? Yeah, okay.
Can you talk a little bit about beam search? Beam search. Beam, yeah, like one of the part of the local search. So you have like a beam search.
I don't know what you mean. The local search, I don't know.
Like a beam search.
No, I don't know what. For me, local search is very clear. I don't know if you want to. Oh, but beam search. But this is like cutting, like branch and bound, but restricted.
But there are people doing local search in the style of beam search, like accepting not just the best solution or one next solution, but a whole range, and then looking at their neighbors and restricting again.
Yeah.
There are people doing that. I cannot give you a reference right
See, now I know what beam search is. It's like doing branch and bound, but just, you know, not looking for all possibles and then look at this. We never put them inside the iterated local search, because local search is like it is a little bit different from beam search. By beam search, you get all the branches and then you choose which ones you do. Maybe mixing the two is a good idea, but this is a good, people doing this, yeah. Yeah, so, okay. Sarah.
Thank you for your nice presentation. Thomas also had a paper with Ruben about iterated greedy. I don't know, you know it? It's the same like as ELS. Most of the time, Angel and I discuss about this. It could be like a subset of the ELS.
I will never get in trouble with Ruben. Yeah, I mean, this is the problem with the names. I say, so greedy is like a local search, but the perturbation is destruction construction. So as I said, some people understood iterated local search like we have a lower level neighborhood on the local search and one move of a higher level on the perturbation. For me, this is one possibility. Anything that you do on the perturbation gets on the structure of the iterated local search, for me. Maybe, you know, he wants to call a greedy algorithm like this, it's okay, it's a good technique, but I will never dare to discuss with Ruben if this is, for me, it gets inside the structure of iterated local search. But some people think it's not. But for me, as one of the, you know, it's, so like I said, like exact methods on the perturbation, like, you know, do some beam search, you know. The idea is that the solution structure is different from the previous one. That's my idea. So for me, we'll get in the structure of iterated local search. If you want to call it any other name, I will never, you know, reject the paper because the name is not the name of the things. I don't care what name they put it. Because the idea is the structure, what is behind the algorithm. Okay? So I think now we deserve a coffee break. Nice coffee break outside. Okay, thank you.